Okay, so this will be the last lecture over chapter 4 over the free radical reactions. And so what we'll do in this lecture is we'll take just some examples of reactions and see if we can predict the major product. And then a few other exercises just to build on that. So if we take this molecule A and do a free radical bromination, so Br2 and heat our light, then where's the bromine going to go? So how many different places could it go? So it could go there, A, we'll call, so those positions are equivalent, right? Or it could go here to B, or it could go to C. How about D? Can't go to D, right, because there's no hydrogen there. And this position is equivalent to that, E, F, or it could go to G. So 1, 2, 3, 4, 5, 6 possible places that the bromine can go. Where's it going to go? Well, where's the best place to put a free radical at? So this A is primary, B is tertiary, C is secondary and benzoic. And then E, F, and G are all aryl. So the worst place to put a free radical is aryl. So it's definitely not going to go there. And then if you remember, benzoic is better than tertiary, so the bromine is going to go to carbon C. So predicting the major product is basically, writing the major product is easy. So just write your carbon structure again, and then attach bromine to carbon C. So just a new line to bromine. So basically, carbon C had 2 hydrogens, right? You took 1 hydrogen off and added a bromine, and that's your major organic product. All right, you also make a molecule of HBr, but you don't have to show that. If the directions say predict the major organic product, that is the only thing that you have to write. Okay, so molecule B, we did that on the last lecture. So you could put the chlorine here, but that's a primary position, and that's equivalent to that. So it could go there, A, or it could go here to B, that's a tertiary position. It could go here to C, that's a secondary position, or it could go to D, that's a primary position. So 4 possible products, and it's going to want to go to C at the tertiary position because, so in the course of this reaction, you would make that tertiary free radical if you were sketching the mechanism, and then the chlorine's going to end up there, so that's the major organic product. Okay, so for C, where's the bromine going to go? Oh, sorry, this should be Br2. So let's see, we'll call that A, B, C, D, E, F, and G, and then this is E also, right? Those 2 positions are equivalent, and those 2 F positions are equivalent. So where's the bromine going to go? Well, where's the most stable place to put a free radical at? So A would be primary, B secondary, C secondary, D is tertiary. That's secondary, secondary, and secondary. So it's going to go to D because that's the tertiary position. That would be the best place to put a free radical at. So that would be your major organic product. Okay, so how about D? So let's see. So that's the most substituted position. So is that where it's going to go? Put a chlorine there. So does that look right, or something looks wrong with that? So hopefully you recognize that that is not right because that carbon has 5 bonds. And you can't put 5 bonds on carbon, right? So this position has no hydrogen there. That's a quaternary position. So you need to have a hydrogen on the carbon in order for the halogen to, for the free radical halogen to take the hydrogen off, and then the halogen can attach there. So it can't go there. So then you're left with A, B, and this is equivalent, A and B, right? Those positions are equivalent. And then C, which is equivalent to that position. So where's it going to go? So A is primary, B is secondary, C is primary, so it's going to go to B. Either of the B positions would give you the same molecule. So take a hydrogen off of B and put a chlorine there, and then that would be your major organic product. Okay, so for E, so that position is secondary and analytic, right? whereas this is primary, and this is vinyl, and that's vinyl. And aryl and vinyl was the worst places to put a free radical, so you don't want to put the chlorine there. You would want to put it in the secondary allelic position. So take a hydrogen off of there and put a bromine on, so that's your major organic product. You also get this side product, which we're going to show a mechanism for in a little bit. So you also get some of that. So that's the major product, and that's the minor product. So at the end of this lecture, let's write a mechanism for this reaction and explain how you make both the major product and the minor product. Okay, so another way that you may see me ask questions in this chapter, so I give you a starting material and ask you to sketch all possible monobromination products. So here you'd want to recognize you could put the bromine there. We'll call that 1, 2, 3, or 4, and that's equivalent to that position, right? So there's 4 possible products. So let's sketch the carbon structure again, and then attach the bromine. So it could go to carbon 1, so we need a new line, and then attach the bromine to carbon 1, or we could put it on carbon 2, or we could put it on carbon 3, or we could put it on carbon 4, right? And that would be 4 different products. Those are all constitutional isomers of each other. But what if I ask the question like this? Sketch all possible monobromination products, including stereoisomers. So this is a little bit trickier. So if we go back to these 4 possible products that you made, are any of them potentially, well, do any of them have a chiral carbon? And so what you'd want to recognize is that there's no chiral carbons here in that molecule. But there is in this molecule. That's a chiral carbon, which means there's a possibility of R and S isomers there. And for this molecule, there's no chiral carbons. But for this molecule, there is. That is a chiral carbon. So you have a possibility of R and S isomers here. Okay, so then that's going to be 6 possible products, right? 1 from putting the bromine at carbon 1. Well, as I have, it's not, when I say 1, that's not, if you were naming the molecule, that wouldn't be carbon 1, right? Carbon 4 would actually be carbon 1. I'm just talking about position 1, position 2, position 3, or position 4. So you can put the bromine at position 1, that's 1 product. If you put the bromine at position 2, there's 2 products there, R and S, so that's 3 total now. Or you could put the bromine at position 3, or you could put the bromine at position 4, and then there's going to be 2 products there, so there's going to be 6 total now. So what do those 6 look like? So we could have put the bromine there at position 1, or we could have put the bromine at this carbon, and that's going to be chiral. So we could have put the bromine there and the hydrogen there, or the hydrogen there and the bromine could have been there. So this would be the R isomer, and this would be the S isomer. Or we could have put the bromine there, which is not chiral. Or the other possibility, let's see, if we put the bromine here, then this carbon with the methyl group is chiral. So to illustrate the stereochemistry there, that methyl group could be forward. Or the methyl group could be back. And so in terms of stereochemistry here, so let's see, this is priority 1, 2, 3, and 4. And that's 1, 2, 3 counterclockwise. So this would be in the S isomer, and this would have been the R isomer. So there's 4 possible constitutional isomers, so if the molecules are drawn like this, it does not show stereochemistry because it doesn't show 3 dimensions. But if you're asked to show stereoisomers, then you need to show 3 dimensions, and you have to recognize, well, which molecules have chiral carbons, because any molecule that has 1 chiral carbon has both an R and S isomer. Any molecule that has 2 chiral carbons is much more complex, because then there's 4 stereoisomers, right? RR, RS, SR, and SS. But we'll probably keep it more simple like this. So if you factor in stereoisomers, then there's 6 possible, 6 different molecules. Right? Still 4 constitutional isomers, but 2 pairs of enantiomers, right? These 2 molecules would be enantiomers, and these 2 molecules would be enantiomers. Okay, so for this reaction, so if you have anytime you're reacting at an allylic position, there's going to be more than 1 possible product, as I've illustrated here. So let's write a mechanism for this reaction that explains how did we make both the major and the minor product. So the mechanism for this reaction, if you remember the first step in a free radical mechanism, so if we heat this up, then that's going to break the bromine-bromine bond, and you would make 2 bromine radicals. So that's an initiation step. And then what's going to happen, so let's sketch out these 2 hydrogens on the allylic position, because one of the bromine radicals needs to take one of those hydrogens. So now let's take one of these hydrogens, doesn't matter which one, and the other electron in the bond will become a free radical on the carbon. Right, so now you have a molecule of HBr, and now you have the alkyl radical, and then what is that going to do? So I'm going to draw this molecule twice, because it can do one of 2 things. So it could react with another molecule of Br2. So it could abstract a bromine atom. So that's your major product. And then a bromine radical would be formed as well. Or what we could do with this is if we take this and draw a resonance structure. So we can move that there and move one of these over, and the other free radical, electron stays behind on the carbon as a free radical. So now the double bond is here, and now the radical is there. And now that you have that, that could react with a molecule of Br2. So take that radical, pull off a bromine atom, and make another bromine radical. And then there's your minor product. Okay, so just you have to keep in mind, anytime you have an allylic radical, it has another resonance structure. So that would lead to 2 possible products. And the major product, of course, this one is a secondary in a allylic free radical. So it's more stable than this one, which is primary and allylic. So this is going to lead to the minor product, and the one that's more stable is going to lead to the major product. So that's the mechanism that shows how the 2 products are formed. And if you wanted to complete this mechanism, we could show termination steps. So if we sketch those termination steps, so this is a little bit more complex because there's more possibilities. So there's 3 different radicals now. And so let's call this A, B, and C. So if you remember termination steps, 2 radicals react with each other. So how many possible combinations there are? So A could react with A, or A could react with B, or A could react with C. So there's 3 possible products. Or B could react with A, but that's the same thing as AB. Or B could react with C, so that would be new. And then C could react with A, but that's the same thing as AC. Or C could react with B, well, sorry, we didn't do BB. Let's back up just a minute. So B could react with itself, or B could react with A, which will be the same thing as AB, or B could react with C. And then C could react with A, which is the same thing as AC, or C could react with B, which is the same thing as BC, or C could react with itself. So that would be CC. So that's 6 possible termination products. So if we just sketch those right quick. So 2 bromines could react with each other to reform Br2. So that's what I mean by AA. Or bromine radical A could react with B, which just happens to make more product, so that's what I mean by AB. Or bromine radical could react with C, which just happens to make more minor product, that's what I mean by AC. Right, or 2 Bs could react with each other. So basically make a bond between those 2 carbons. So the easiest way to sketch this, let's just sketch the 2 radicals again. So then we're going to get rid of the 2 radicals and make a bond between those 2 carbons. Right, it doesn't have to look pretty, you just got to get the bonds in the right spot. So that's what I mean by BB. Right, or B could react with C. So we can make a bond between these 2 carbons. So if we just draw those 2 radicals again, and then we're going to get rid of the 2 radicals, and we're going to make a bond between those 2 carbons, right? So that doesn't look pretty, but that's what I mean by BC. If we want to draw that more pretty, then that goes to CH2, and then there's an alkene, right? That's the same thing. And then the other possibility is 2 Cs could react with each other. So we can make a bond between these 2 carbons. So again, if we just draw these 2 carbon structures again, and we're going to make a bond between these 2 carbons, and that's what the CC product, termination product, would look like. Or if we drew that prettier, so let's see, 1, 2 CH2s, then there's a double bond. That would be the same thing as that, right? So that's 1, 2, 3, 4, 5, 6, 7, 8 carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8 carbons, right? Okay, so that would be the full mechanism for this reaction. And, okay, so yeah, so free radical mechanisms can be pretty long, pretty complex, but that's the basics. You always have an initiation step where you make free radicals, and then the free radical halogen takes a hydrogen off of the molecule to make an alkyl radical, and then the alkyl radical reacts with the Cl2 or Br2 to put the chlorine or bromine on the molecule. And then maybe you just show termination steps at that point. It all depends on what the question is, right? And how complex the reaction is. In this case, it's a little bit more complex because there's 2 possible monohalogenation products. Okay, so that's it for this material. Hopefully that made sense.